So today we have with us Eliran, and he will be speaking on verifiable relation sharing and multi-verifier zero knowledge in 2 rounds, trading NIJX with honest majority. And so he is a PhD student at Tel Aviv University, working with Benny Applebaum. And just to give a personal touch, I mean, it was my distinct pleasure to work with Eliran over several works. And I'm very happy to welcome him in this seminar series. And in fact, today he's going to talk about one of our joint works. Over to you, Eliran.
Yes, so thank you very much, and thanks for inviting me. And so today I'll talk about a joint work with Benny Applebaum and with Arpita about about verifiable relation sharing and multi-verifier zero knowledge in 2 rounds. And I will show that if we have an honest majority, then we have a substitute for non-interactive zero knowledge from weak assumptions. And I will start by discussing multi-verifier zero knowledge, or MVZK. So as you know, in the standard settings of zero knowledge proofs, we have one prover and one verifier. And the prover wants to prove to the verifier that the statement X is true, but without revealing any information about the secret witness W. And we require the standards correctness, soundness, and zero knowledge properties. In this work, we consider a variant of zero knowledge where we have one prover but many verifiers. And now the prover wants to prove to all the verifiers that the statement X is true, but without revealing any private information. This can be seen as the dual of multi-prover zero knowledge. And this is in fact a common scenario in multi-party computation where we have one party that wants to prove some statement to the other parties, but without revealing any private information. To formalize what we require, I use ideal functionalities. And for those of you who are not used to work with ideal functionalities, then just think of it as a box that helps me to formalize the requirements from MVZK. Okay, so what MVZK does, I want it to take the input and the secret witness from the prover. Now, if the relation R is satisfied, if the statement X is true, then I want it to return the statement X to all the verifiers. And this means, in this case, the verifiers know that the statement X is true. And notice that the verifiers have no information at all about the secret witness W. Okay, so if the relation is satisfied, the verifiers should know that the statement X is true. However, if the relation is not satisfied, then the verifiers should receive a special symbol that tells them that the prover tried to cheat. Okay, so this is the MVZK functionality. This is what we want to implement. And, and in order to implement it, we assume that the parties can communicate over secure channels, and also that they have access to a broadcast channel that let them send a single message to the rest of the parties, so that all the parties receive this message. So this is the communication model, and we require full security even against an active adversary that can deviate from the protocol. Okay, this provides very strong security guarantees. For example, it provides a strong completeness notion. So for an honest prover, the honest prover can convince the honest verifiers that the statement is true, even if some of the verifiers are corrupt. So we have completeness even if some of the verifiers are corrupt. And it also implies simulation-based zero knowledge, which essentially means that the corrupt verifiers have no information about the secret witness W. And it also provides a soundness with knowledge extraction. And by soundness, I mean that the corrupt prover cannot convince the honest verifiers that the false statement X is true, even if some of the verifiers are corrupt. Okay, so if the corrupt prover, even if he colludes with some of the corrupt verifiers, he still cannot convince the honest verifiers that the false statement X is true. And like I said, we also obtain knowledge extraction, which means that if the prover convince the honest verifiers that the statement X is true, which means that the statement X is indeed true, then the secret witness can be efficiently extracted from the joint view of the honest verifiers. So those are some of the guarantees of full security against an active adversary. And in this work, we studied the round complexity of protocols that provide those guarantees. So we ask how many rounds are required. And in fact, in this work, we are mainly interested in a two-round protocol for MVZK. So we require a two-round protocol that provides full security against an active adversary. And it turns out that if you don't have an honest majority, then you cannot get an MVZK protocol in 2 rounds. Okay, so a 2-round protocol exists only for languages in BPP. And this follows from the classic work of Gondrich and Doren. However, if you have access to a trusted setup, in this case to a common random string, then it is known that you can obtain a one-step protocol for all of NP, right? A protocol in which only the prover speaks. And this is just an uninteractive zero knowledge. And you can obtain it either from a public key assumptions or in the random oracle model. Right, but again, this requires a trusted setup. In the plain model, you can show that there is no 2-round MVZK protocol for NP, assuming that VP is not equal to NP. So since we cannot have MVZK in 2 rounds without honest majority, we move to honest majority, and it turns out that if you have an honest majority, then you can obtain MVZK protocol in 2 rounds. So again, it is not hard to see that a 1-round protocol exists only for BPP, but now you can obtain a 2-round protocol for all of NP. And so such a protocol appears implicitly in the work of Groth and Ostrovsky, and it requires public key encryption and non-interactive zero knowledge. And in fact, this protocol has this nice feature that the first round is input independent, which means that the prover can which means that the parties can execute the protocol even before the prover knows the statement and the witness, which are only required for the second round. Okay, so the first round can be executed before the prover knows the inputs. So this is a nice feature to have. But as you can see, the assumptions required for this construction are essentially the same assumptions that are required for non-interactive zero knowledge, or maybe even stronger assumptions like public key encryption. And therefore, a natural question is, can we obtain a 2-round MVZK? Can we use the fact that we have an honest majority in order to obtain a 2-round MVZK protocol without non-interactive zero knowledge and public key encryption? And maybe we can even obtain such a protocol by using only minicrypt type assumptions because we have an honest majority now. So this is the question that we ask in this work, and we show that it is possible. So we show that we can obtain a 2-round protocol for minicrypt type assumptions. So here are the results. We assume the existence of non-interactive commitments, and in a minute I will say what the exact assumption is, but this is a minicrypt type assumption. And we construct a 2-round MVZK protocol, again with this nice feature of offline and online rounds, so that if the number of parties is constant, then we obtain optimal resiliency for honest majority, which means that the number of corrupt parties T should be less than 1/2 the number of parties N. And if the number of parties is a polynomial in the security parameter, then we obtain almost optimal resiliency. We require a little bit more than honest majority. Okay, so those are the main results regarding MVZK. And I want to highlight the case of one prover, 2 verifiers, and a single corruption, just one corruption. Okay, and our theorem says that you can obtain an MVZK protocol in 2 rounds for this case by using only minicrypt type assumptions. Okay, so by adding just a single verifier to the standard settings of zero knowledge, you can obtain a 2-round MVZK protocol for minicrypt type assumptions. So those are the main results, and I should have said, feel free to ask questions if you have any at any time. So, okay, so those are the main results regarding MVZK, and now let me say a few words about the assumptions about non-interactive commitments. So we have 2 kinds of non-interactive commitments. The first kind is computationally hiding non-interactive commitments. And if we are using this kind of commitments, then we need them to provide some kind of security against selective opening attacks. The good news are that such commitments can be based on minicrypt type assumptions. For example, on injective 1V functions with sub-exponential hardness, or even standard 1V functions with sub-exponential hardness together with a common random string. And in fact, you don't actually need a common random string. You can replace it with the randomization assumptions. Okay, so by using either the first assumption here or the third assumption here, you obtain a two-round MVZK protocol in the plain model and for minicrypt type assumptions. So the second kind of commitments is statistically hiding non-interactive commitments. And if we are using this kind of commitments, then we even provide a stronger notion of security that is called everlasting security. And the everlasting security can be seen as a security notion between computational security and information theoretic security. And it means that the protocol is secure against an adversary that is bounded during the execution, which is the standard, but then the adversary can be computationally unbounded after the execution of the protocol, which is more similar to information theoretic security. Okay, so it means that it doesn't matter how much time and effort the adversary invests after the execution of the protocol, he still cannot break the security of the protocol. So this is everlasting security, and if we are using statistically hiding non-interactive commitments, then we obtain everlasting security. Now, such commitments can be based on collision-resistant hash functions, which is, again, a minicrypt type assumption. However, I should mention that there is a technicality here regarding how we select this hash function. So because the adversary is non-uniform, the hash function has to be picked from a family of hash functions, and you should pick this hash function before the execution of the protocol. Okay, so one way to do it is to use a trusted setup, a common random string that just picks a random hash function. An alternative is to have an additional offline round in which the parties select this hash function. And finally, if the adversary is uniform, then the hash function can be fixed and there is no need for a trusted setup. Okay, so those are statistically hiding non-interactive commitments, and the main point is that if we are using this kind of commitments, then we obtain a two-round protocol with everlasting security. I mentioned an application of MVZK, and I want you to notice that MVZK captures an important feature of non-interactive zero-knowledge, which is the minimal round complexity of non-interactive zero-knowledge. So if you have an honest majority, you can think of our MVZK protocol as a substitute for non-interactive zero-knowledge, where the CRS of the non-interactive zero-knowledge is replaced with a single offline round that does not depend on the inputs, and then the proof requires only one round. And in addition, we provide the UC security, so you can just take our MVZK protocol and plug it into your protocols instead of non-interactive zero-knowledge. And the main point, of course, is that we get all of this from weak assumptions, only for minicrypt type assumptions. Okay, so the main point here is that if you have an honest majority, you don't need non-interactive zero-knowledge. You can replace it with our protocol that uses only minicrypt type assumptions. Good, so any questions? So this was MVZK. And in fact, in the paper, we study a more general primitive that we call verifiable relation sharing, or VRS. So far, we assume that everyone knows the same statement, right? The verifiers and the prover agree on the statement. But what happens if the statement X is distributed among the verifiers? So it is shared among the verifiers, and now the prover wants to prove that the shared statement X is true, but without revealing any additional information to the verifiers except from the shares they already know. And so this is actually a scenario that occurs in many cases in multi-party computation, in private data aggregation, and in anonymous communication. And I do want to mention the work of Bonnet, Boeing, Corrigan, Gibbs, Gilboa, and Ishai that initiated a formal study of zero-knowledge proofs over shared data. Just like before, we formalized the requirements from VRS by using an ideal functionality that is parameterized with a relation R. And now the prover inputs the secret witness and also the shares of the verifier. So those are the shares of the verifiers. And if the relation is satisfied, then every verifier just receives its own share. Okay, so Mr. Brown here received the first share and Mr. Yamo received the second share and so on. Right, so every verifier only knows his own share, but he has no information about the secret witness or about the shares of the other parties. And the other case is when the relation is not satisfied, and in this case again, the verifiers should know that the prover tried to cheat. So they receive a special symbol that tells them that the prover tried to cheat. So this is the VRS functionality. And just like before that, I want to mention that it captures and generalizes several cryptographic primitives, such as verifiable secret sharing, secure multicast, multi-verifier zero knowledge that we've just discussed, and the zero knowledge proofs over shared data of Boneta. Right, and it has many more applications. Before we wanted to implement this box of VRS, and we assume the existence of honest majority, we've seen that without an honest majority, we cannot obtain a two-round protocol. And we require, just like before, full security against an active adversary that can deviate from the protocol. And again, we obtain those strong completeness notion. So in VRS, the completeness means that the honest prover can convince the honest verifiers that the share that they received are correct, even in the presence of some corrupt verifiers. Okay, so we have completeness again, even in the presence of corrupt verifiers. We obtain simulation-based security, which means that the corrupt verifiers only have information about their shares, but they have no information about the secret witness or about the shares of the honest verifiers. And again, we obtain soundness with knowledge extraction. And soundness now means that whenever it means that the honest verifiers only accept the shares if the relation is satisfied. And the knowledge extraction means that if the honest parties accepted the shares, then the secret witness and in fact all the private information of the corrupt prover can be efficiently extracted from the joint view of the honest verifiers. Okay. So those are again the same guarantees as before, and again we studied the round complexity of verifiable relation sharing. Let me tell you what is known about the round complexity of verifiable relation sharing, and let me start with information theoretic security. So it turns out that verifiable relation sharing VRS cannot be implemented in 2 rounds with statistical security. So this is from an unpublished work, again with Benny and with Arpita. So again, with information theoretic security, you cannot obtain a VRS in 2 rounds. And therefore, we move to the computational settings.
Eliran, there is a question. Ananya, you can unmute yourself and ask directly. Ananya, are you there?
Okay, yeah, I'm hearing you.
Okay.
But I can't see the question, I mean.
Okay, so the question is, do we consider honest majority including the prover or only amongst the verifiers?
Yes, so it includes the prover. I look at an honest majority among all the parties here. Okay, so a majority of the parties here should be honest, and it includes the prover, yes. Any other question? Okay.
No.
Okay. So, like I said, with information theoretic security, you cannot obtain a 2-round protocol for verifiable relation sharing, and therefore we move to computational security. And in the computational setting, the best upper bound that we have is the 3-round protocol of ACGJ that provides computational security, and it requires public key encryption and non-interactive zero knowledge. Okay, and this is in fact not a special protocol for verifiable secret sharing. This is a protocol for general MPC. Okay, so we don't know if it is possible to do something better for verifiable relation sharing. And there is also a lower bound that shows that a 1-round VRS is impossible, and this is not, it's not hard to see that this is true. Okay, but as you can see, the question of a 2-round VRS protocol is completely open. And of course, the question of a 2-round VRS protocol that does not require public key encryption and non-interactive zero knowledge is also open. Okay, and this is again the question that we study in this paper. And the results regarding VRS are essentially the same results regarding MVZK. So we assume the existence of non-interactive commitments. Those are the same assumptions as before. And we construct a 2-round VRS, again with offline online round. So that again, if the number of parties is constant, we obtain optimal resiliency for honest majority. And if the number of parties is polynomial in the security parameter, then we obtain almost optimal resiliency. We require a little bit more than honest majority here. So those are the same results as in MVZK. Now VRS has many applications. And in a follow-up work, again, this is another work with Benny and Arpita, we show that we can use our VRS protocol in order to construct a round-optimal multi-party computation protocol from minikrypt type assumptions. So we construct a two-round protocol for honest majority that provides full security, and we use the same assumptions that we use in this paper. Okay, previous works, like I've mentioned, require public key encryption and non-interactive zero knowledge. There are more applications. I do want to mention that verifiable relation sharing turns out to be equivalent to single input functionalities. Now, single input functionalities are just functionalities that take input from a single party and then provide the outputs to the rest of the parties. Right? So VRS is just a special case of single input functionalities because only the prover has an input. However, every single input functionality can be translated into a VRS, and therefore these two are equivalent. And this means that for every single input functionality, we can obtain a two-round protocol from minikrypt type assumptions. So this was those are the results, and now I planned to talk about the proof idea, but Arpita, I'm not sure. Should I talk about the proof idea? Arpita? Okay, so this is the technical part. It will be a little bit more complicated, but let's start with it. Okay, so I'm making a simplifying assumption here. I assume that I have this nice box, this magic box that for verifiable secret sharing. And what does it mean? It means that the prover can input a secret S to this magic box. And this magic box samples a random degree T polynomial f of x whose free coefficient is the secret. And it generates the Shamir shares by using these polynomials, right? So those are just the Shamir shares of the secret S by using those polynomials. Okay, now think of those as public commitments. So it publicly commits to the Shamir shares of the secret S, and it gives every verifier an opening to one of the commitments. Okay, so Mr. Brown obtains an opening to the Brown commitment, Mr. Yellow obtains an opening to the Yellow commitment, and so on. So this is essentially Shamir secret sharing, but with publicly shared, with publicly committed shares. Okay, so the shares are publicly committed, and every verifier has an opening to exactly one share. So for this talk, I'm making this simplifying assumption. I assume that I have this magic box. In the paper, we actually need to implement this box in a two-round protocol, and it just adds more complications. So for this talk, let's assume that I have this box. Like I said, it implements essentially Shamir secret sharing, so it means that T verifiers have no information about the secret S, but T+1 verifiers can recover the secret S. And another important feature is that the verifiers can either open the correct shares or an erasure. Because those are public commitments, Mr. Brown can either provide the correct opening to these commitments, which will open the correct shares, or some bad opening that will open to an erasure, right? It cannot open any other value than the correct share. Of course, this magic box ensures that even for a corrupt prover, the outputs will be well-formed. Okay, the commitments will correspond to a degree T polynomial. Okay, so this is the first assumption that I am making for this talk. The second assumption is that I have homomorphic commitments. Right, the problem with this secret sharing scheme is that it is not linear. Standard non-interactive commitments are not homomorphic, and therefore this secret sharing scheme is not linear. And therefore, just for this talk, I assume that I have homomorphic commitment, which means that I have a linear secret sharing scheme here. In the paper, we actually work quite hard in order to get rid of this assumption, and we develop protocols that perform round-efficient linear operations over non-homomorphic commitments. happen, but again, for this talk, I'm making this assumption. So just to summarize, I assume that I have this magic box, and I assume that I have homomorphic commitments, but like I said in the paper, we need to work hard in order to get rid of these assumptions. So I'll discuss about the heart of the construction, which is just a special case of VRS. This is a protocol for triple secret sharing. And what is triple secret sharing? Like I said, it's a special case of VRS where the prover wants to share a triple A, B, and C, and also prove that C is equal to AB. This is also known as a Beaver triple. And what does it mean? It means that the prover inputs the triple to the functionality, and if C is equal to AB, then the functionality generates a sharing of A, a sharing of B, and a sharing of C by using the same secret sharing scheme that we've just seen. And otherwise, if C is not equal to AB, then it lets all the prover knows, all the verifiers know that the prover tried to cheat. Okay, so this is triple secret sharing. And I wanted to run protocol for triple secret sharing. And I will start by describing a 3-round protocol for triple secret sharing, and then I will explain how to reduce 1 round. So in the first round of the protocol, the prover picks random polynomials a of x and b of x, whose free coefficients are a and b. Those are degree d polynomials where d should be large enough. And he also computes the polynomial c of x, which is just the multiplication of a of x with b of x. Okay, and if the prover is honest, then the free coefficient of the polynomial c of x is c, which is a times b. And in the first round, he just looks at the coefficients of every polynomial, and he shares those coefficients by using the magic box. Okay, so this is the free coefficient of the polynomial a of x, and he shares this coefficient by using the magic box, and it does so for every coefficient of the polynomial a of x, for every coefficient of the polynomial b of x, and for the coefficients of the polynomial c of x. Okay, so at the end of the executions, the parties see all those public commitments, and for every coefficient, every verifier has exactly 1 share. Okay, so now the coefficients are shared among the verifiers. This is the first round. And I want you to notice that A, B, and C are already shared, right? A is just the free coefficient of A of x, B is the free coefficient of B of x, and C is just the free coefficient of C of x. Therefore, it only remains to prove that C is equal to AB. Now, the main idea is to prove that, is to know that we can actually prove that C of x is equal to f x times B of x. And in order to do so, we'll pick a random point alpha. We will compute the polynomials on the point alpha, so we'll compute a of alpha, b of alpha, and c of alpha, and we will verify that c of alpha is indeed equal to a of alpha times b of alpha. Okay, and for an honest prover, this is always true because c of x is by definition equal to a of x times b of x. But for corrupt provers, if c of x is not equal to a of x times b of x, then the parties will see inequality here with very high probability. Okay, so this is the main idea. And this is what we do. So in the second round, we let every verifier to generate a random challenge. This is just a random field element, which is not 0. And in the third round, we let the parties compute the a of alpha I, b of alpha I, and c of alpha I for every challenge alpha I, and verify that c of alpha I is indeed equal to a of alpha I times b of alpha I. Now, in order to compute those values, we use the fact that we have homomorphic commitments. Okay, so I want you to notice that a of alpha is just a linear function of the coefficients of the polynomial a of x. Now, those coefficients are shared among the parties. And if I'm taking Mr. Brown as an example, I can apply the same function on the public commitments to the Brown shares of the coefficient and obtain a commitment to the share of a of alpha I. Right, so again, I just applied the same linear function on the Brown shares of those coefficients, and I obtain the commitment to the share of Mr. Brown on a of alpha I. Okay, so we do the same trick for each of these parties. So now for each of these parties, we can locally compute commitments of those shares. And now an honest party will provide us with the correct opening to this value. So and because we have an honest majority, we have at least t plus 1 correct shares. Now corrupt parties, because we have binding commitments, can either open the correct share or an erasure. Okay, so again, this means that we have at least t plus 1 correct shares, So we can recover A of alpha by using all the correct shares that we get. Okay, so in this way, we compute A of alpha, B of alpha, and C of alpha, and finally we can verify that this equation is true. If it is not true, then we reject the proof. If it is true, then we accept the proof. Okay, so this is our 3-round protocol for triple secret sharing. And we have completeness because for an honest prover, the polynomial C of x is equal to A of x, so this equation is true. We have privacy because the only thing that the adversary can see is an evaluation on those polynomials on non-zero points. And therefore, if the degree d is large enough, then just like in Shamir secret sharing, the free coefficients a, b, and c remain private. Finally, to see that we have soundness, I want you to notice that if c is not equal to a times b, then the free coefficient of the polynomial c of x is not equal to the free coefficient of a of x times the free coefficient of b of x, which means that the polynomial c of x is not equal to a of x times b of x. Okay, and therefore, if we take a random field element and evaluate those polynomials at this field element, then with high probability we see inequality here. Okay, and this is why we have soundness with very high probability. Okay, so this is our 3-round protocol for triple secret sharing, but like I said, what we actually want to get is a 2-round protocol. Okay, so some of you probably ask now, why not use the Fiat-Shamir heuristic? And the reason is that I don't want to use the strong assumptions. Okay, I want a 2-round protocol for mini-crypt type assumptions. And I will show you that because we have an honest majority, we actually have a substitute to the Fiat-Shamir heuristic. So what we would like to do is to somehow generate the challenges in the first round as well. Right, so the naive approach is indeed to let every verifier to broadcast the challenges already in the first round at the same time that the prover generates the polynomials a of x, b of x, and c of x. Right, this is the naive approach. However, this protocol turns out not to be secure. And the reason is that in multi-party computation, we usually consider a rushing adversary. And a rushing adversary in every round can first see the messages of the honest parties and only then send the messages of the corrupt parties. Now, in our context, it means that the corrupt prover can first see the challenges that are generated by the verifiers and only then pick the polynomials a of x, b of x, and c of x. And the problem with that is that given the challenges, it is not hard to construct polynomials that pass every challenge, but do not satisfy that the free coefficient of c is equal to the multiplication of the free coefficient of a and b. Okay, so we have a problem with the soundness in this case. I should mention that this protocol is actually secure if the adversary is not rushing. Okay, but for a rushing adversary, this protocol is not secure, so we need to find another way to generate the challenges. And indeed, we will generate the challenges in the first round, but in a way that keeps at least one challenge secure from the adversary. So I will start with the toy version. So let's assume for the toy version that I know the identity of the corrupt parties. Okay, so the honest parties know who the honest parties are, and they know that these two are corrupt. So in the first round, I let the prover to generate the polynomials a of x, b of x, and c of x, just like before. But now I also let one of the honest verifiers to generate a secret challenge that will be sent only to the honest verifiers by using the private channels. Okay, so now this secret challenge alpha is not known to the adversary, which means that alpha is independent of the polynomial a of x, b of x, and c of x. So this is the first round. And in the second round, I just require from the honest verifiers to open their shares of a of alpha, b of alpha, and c of alpha. Right, so all the honest verifiers open their shares of a of alpha, b of alpha, and c of alpha. Now, because I have an honest majority, I'm guaranteed to have at least t plus 1 shares, and therefore I can recover those values and verify that c of alpha is indeed equal to a of alpha times b of alpha. Now, the same analysis as before shows that this protocol is indeed secure. Well, for the soundness, I use the fact that alpha is independent of a of x, b of x, and c of x. So this is the toy version. Of course, we do not know the identity of the corrupt parties, and we do not know who the honest parties are. But the main idea remains the same. We just do it the same thing now for every set S of t plus 1 parties. Okay, so for every set S of t plus 1 parties, we do the same for this set, and also for this set, we do the same thing. Okay, right, so for every set, we let one of the parties to generate a secret challenge. And in the second round, we require from the parties to open their shares of the evaluations of the polynomials on this challenge. Right, so for every set of t plus 1 parties, we do the same thing. Now, of course, most of the sets contain at least one corrupt party, and this corrupt party can sabotage, each of these two steps. So if this party is the one generating the secret challenge, then it can, for example, send different challenges to different parties, and in the second round, it can refuse to open the share. But the main point is that I have at least one set that contains t plus 1 honest verifiers, and this set guarantees that I have a soundness. Okay, so this is our protocol for this is our two-round protocol for triple secret sharing, and the reason that we use it only for a small number of parties is that the number of set is n choose t plus 1, so it is exponential in the number of parties. Right, so this protocol is only efficient for a small number of parties. In order to obtain a protocol that is efficient for a large number of parties, we need to use this protocol in order to construct a VRS for many parties. So we have a transformation that I think that I will skip, and I will just move to the conclusion. So let me very quickly summarize what we've seen. So we've discussed verifiable relation sharing and multi-verifier zero knowledge. We've seen that if we have an honest majority, then we can construct a two-round protocol for these primitives for minikrypt type assumptions, and even with this nice feature of offline and online rounds. We've discussed everlasting security, and we've seen a version that of MVZK and VRS that provides everlasting security. And I didn't talk about how we construct these round-efficient linear operations over non-homomorphic commitments, and I also skipped now the protocol for VRS with many parties. And finally, there are several open questions. For example, can we obtain optimal resiliency for many parties? Right, so now if we have many parties, then we obtain almost optimal resiliency, but can we push it a little bit further to optimal resiliency? And can we relax the requirements? For example, can we get rid of the sub-exponential hardness? And regarding everlasting security, can we do it without a CRS and maybe even from one-way functions? Okay, so thank you very much for your time.